Hi, this is Robert Lamens, and I am partnered with Landon Gerald, Claire Pearson, and Yassine Fajal, and this is our final presentation for the dual lander Mars Ascent vehicle for AE6372.
In 1969, the lunar landing occurred with Neil Armstrong stepping foot on the surface of the moon. 26 years ago, Mars Pathfinder was the first successful rover to land on Mars. More missions have been successful to Mars, with Curiosity and Perseverance to look at the prospects of life once existent on the planet. Recent developments are to have manned missions to Mars in the recent future. The big picture is to develop a dual Mars lander ascent vehicle to have reliability and features for human and scientific interplanetary research. The goal for this mission is to enhance the processing and telemetry for better feedback control, while expanding the capacity to support life and increase samples. Throughout the mission, we want to ensure reliability and safety for astronauts with power and life support systems. Experienced low-cost technology and development and media coverage have incentivized academic research and private companies to work along NASA and international space agencies. As you can see, these are the stakeholders interested in the DLMAV project for Mars. Define the problem. The competitors for this project can be seen below. Russia in 1971 had the first lander on Mars. It lacked control and no data was collected during that mission. In 2021, China launched Zurich. It was a lightweight vehicle and had great navigation but lost power recently. In 2023, NASA launched Perseverance. It had a range of instrumentation and battery support systems. Improvements to it should be the control and computer processing system. New developments are being made by these organizations towards humans landing on Mars. The mission of the dual Mars lander ascent vehicle is broken down into its parts: a successful launch and landing of a dual person crew, enhanced vehicle control to land 1 kilometer from each other and carry 25 metric tons, and finally to return to Earth safely with its samples. Research and science objectives are defined by developing a mid-LD vehicle with an 8.4 diameter, research computer-aided vision to have faster response times than 20 minutes, and to develop the rover for ground fuel transfer support, carry 50 kilograms of unique Mars samples for research. The mission overview of the DLMAV includes Stage 1, the launch, Stage 2, interplanetary travel, Stage 3, landing, Stage 4, sample collection, and Stage 5, ascent back to Earth. In Stage 1, the launch, we see on the right there is our booster stack, which we are using to exit Earth's atmosphere. We have some SRBs, which boost off from our liquid fuel booster stage, which is utilized for our fine-tunement of our orbit of Earth, where we disconnect into the cryogenic propulsion stage for interplanetary travel. Throughout Stage 2, we are conducting interplanetary travel, and at the end, we are orbiting Mars and entering into the Martian atmosphere. There are several things we have to consider. Mars has an atmosphere as a planet, which it's going to conduct drag and heat upon our ship. These are extreme forces that would not be experienced upon things like asteroids or entering the moon. As the craft approaches the surface at suborbital speeds, roughly 12,000 miles per hour relative to the surface, the heat shield technology is going to be utilized for the craft to protect it from extreme temperatures, which would melt any standard material. This protects the vehicle and crew upon descent. So we begin our descent, and we're going to have to kill off an extreme amount of delta V, meaning that we need the parachute deployment in order to do that. The parachute stabilizes our craft, and by that means we are reaching very low velocities relative to the surface. The parachute deployment allows for a speed permissible to the fine-tunement through rocket boosters that give actuated control of the landing. Utilizing the thrusters to fine-tune our exact trajectory relative to our landing point, we begin to fine-tune our landing spot within 1 kilometer of the 2 vehicles. This finalizes the descent stage as we open the lander legs to initialize the landing process. Moving on to Stage 4, Mars sample collection, this is a system view of the mid-LD vehicle designed for landing on Mars. On the surface, the crew will then begin to perform EVA collection of samples and explore the Martian terrain. The rover will be utilized for the fuel transfer operations of the dual vehicles. The MAV launches and starts back the ascent to Earth, going back into orbit. This is the payload for the dual Mars ascent vehicle. Noticeably, the cargo hatch is nice and large. This is for the collection of the 50 kilograms of the unique Mars samples, constraints to the project. Noticeably, you also can see beneath it are the boosters and landing engines visible for the vehicle's descent.
So now we get to the heart of the problem. We have to design a Mars ascent vehicle that is able to take humans from an orbiting station down to the surface of Mars and back up again, along with whatever cargo and samples that may be on board. This will have to be done under certain limitations, such as having a maximum or minimum payload capacity of 25 metric tons, having the lander diameter be within 8.4 meters, along with other limitations.
Hello, this is Landon, and I will now give a concise description of our concept operations. So we have a start on the SLS launch from Earth, which is step 1, and from this we have 2 launches which will deliver a lander each. So we have 2 landers that arrive at the Martian atmosphere in a 8.4 meter diameter fairing, and this fairing will be jettisoned into clamshell form to reveal the 2 landers. And after aerobraking and an entry, descent, and landing phase, the landers are on the surface, and from which the 10 kilowatt reactor, the propellant, the MAV itself, which is stored in one of the lander's cargo bay, and various other mission support elements are deployed. Then in step 3, all these components are assembled, and so the MAV is ready for launch. The samples are inserted, all the relevant systems are working, the propellant transfer is effectuated. Then in step 4, the Mars ascent vehicle launches with the astronauts and the samples on board, and this will be in accordance with our time requirement, which is in 2040. And then in step 5, we have rendezvous with the Deep Space Transit in a 5-sol parking orbit, and then from here, the samples are returned to Earth. And note that the green arrows represent parts that are pertinent to our mission, and then blue, which is mainly the return to Earth, represents things that are not in the scope of our mission, but are included for completeness.
The functional architecture is broken down into propulsion, life support, ground support, GNC, telecommunication, data acquisition, and vehicular design. With an reference input from the ground control, we have our peripheral sensors like the thermocouple altimeter gyroscope to develop our orientation and computer vision, which is fed into a fast Fourier transform correlation algorithm, which is then feedback into the control system to have fine-tuned control.
Hello, everyone. My name is Yassine, and I am one of the team member of the dual Landing Mars ascent vehicle. And in this slide, I'm presenting the QFD Room 1. The focus is the customer requirement for this vehicle. And one of the most significant challenge is the absence of ground structure on Mars, combined with the vacation delay lasting up to 20 minutes. These factors present some of the tough hurdle on our mission. In Room 2, we focus on the engineering characteristics, given that this mission has never been undertaken before. We expect most of the characteristics to be oriented toward improvements. In total, there are, in 3, our focus is on the relationship matrix. The key takeaway highlight the interconnection between engineering characteristics and the customer requirement. All engineering characteristics have at least one strong relationship with the customer requirement, emphasizing the importance of aligning our design with the customer needs. Specifically, customer requirement 1, 2, 3, 4, and 7, as you can see on the slide, demonstrate the strongest relationship with the engineering characteristics. These requirements play a crucial role in guiding our design decision and ensuring that we meet the customer expectation effectively. Furthermore, the engineer characteristics, structural integrity, propulsion system, ADL, GNC, guidance, navigation, and control, life support, and control stability exhibit the strongest relationship with the customer requirement. These characteristics will be a key focal points in our design process to ensure that they align properly with each other and address the customer needs efficiently.
I'm Landon, and we're now going to go over QFD rooms 4 through 7. So here we have room 4. We have interesting findings in which most of the rooms have a positive correlation, and the others have neutral ones. And now here in room 5, we have the interesting revelation that the propulsion system is our top priority, and that everything else is of similar importance, but in any case, we should give most attention to our propulsion development. And now for room 6 and 7, we found that some of the most important criteria are the 10 kilowatt fission surface device, and then also our adherence to launch constraints, such as the 8.4 meter fairing, and also the inclusion of oxygen for the life support system on the MARS7 vehicle and other components of the mission as required.
Hi, this is Robert. So now for the 8th room of our QFD, the competitive assessment. Who would our proposed lander be competing against? So far, only 3 countries have actually had rovers land on Mars: Russia, China, and the US. So if we were to be sponsored by the US government, this lander would have equipment from past Mars missions available to them. However, no other mission in history has been attempted such as this one. This would be by far the largest mass and payload requirements of any previously attempted Mars landing, and would likely be the first ever instance of a crewed lander mission. And although we have similar technologies for sample return on the Perseverance rover, it would be much more advanced than anything we'd ever seen before. Therefore, despite having access to previous technology, requirements such as having the Mars ascent vehicle be able to produce thrust enough to get into orbit all on its own would be extremely difficult. At this point, untested compared to some of the previous Mars missions. However, as you'll see in these slides here, the target values for our lander are only, say, we want the full lander to be have a payload weight of about 25 metric tons, not too much. Whole thing would be about 8.4 meters, so it is within the scope of imagination. So none of this is truly seems out of the scope of possibility.
Hello, this is Landon once again, and I will be talking about establishing value. We start off with some smart high-level requirements, of which we have quite a few, but these are just some examples to showcase that we have quite a variety of parameters we're considering. So we have time factors, such as launch of the MARS7 vehicle by 2040. We have payload requirements, we have power requirements, and so on and so forth. And now we have product and priority evaluation. So we have stakeholder needs and engineering characteristics we considered. So we have NASA strategic plan as one of their main drivers, which is a current version published for this year, which is dictating where most funds are appropriated for NASA projects. It's a very useful resource. And then for engineering characteristics, we have some examples of AIAA announcement opportunities used for this project. And also we have the Mars 2020 goals, in addition to other similar Mars and other planetary missions which allow us to serve as baselines. And then for decomposition to a subsystem level, we have alternatives identified via morphological matrices and other techniques which allow us to come up with a functional decomposition. So this functional architecture presented here has 4 levels of decomposition, which allow us to concretely define our requirements, which leads us to model-based system engineering. So here is just a snippet, a screenshot of our MBSC submission deliverable for the project. And here we see, for instance, our customer requirements defined, which are encapsulated from AIAA. And here's a very specific view of engineering characteristics. We have structures, power, and propulsion here represented in terms of the requirements diagram for our deliverable. On the bottom, we have how our constraints are defined for one of our a couple of equations that are solved. And here we have even more specific view of the thrust equation and the parameters that go into these. So we have a propulsion requirement which we derived, an engine requirement, and a number of engines. So we have thrust and how many engines it would take for us. And then this is all compiled into one big constraint.
Next step in our project is to generate a feasible alternative for our vehicle. And to do that, we had to utilize a morphological matrix. Morphological matrix is super important in early design phase. It's like a handy tool that help us explore and combine different design option for different components of the vehicle. With this tool, we can analyze and pick the best combination of the propulsion systems, material, structural analysis, structural element, and so forth. So this innovative vehicle demands careful consideration of various functions and characteristics, each contributing to its to this mission to be successful. In our morphological matrix table, we have considered 4 different alternatives, from autonomy in altitude control with sensor-based and GPS-based option, to a range of power source like solar, nuclear, radioisotope, thermoelectric generators, and even nuclear fusion. As far as the structural choices, we have got 3 top materials: carbon composite, aluminum alloy, and titanium alloy. Carbon composites are super light and strong, great for spacecraft frames and payload structure. Aluminum alloys has a combination of or a balance between weight and strength, while titanium alloy, on the other hand, has super tough and can handle extreme condition. And on the thrust generation, we have monopropellants, liquid propellants, ion thrusters, utilizing xenon, and monopropellant with hydrazine, with the communication bandwidth ranging from 512 kilobytes per second to 6 megabyte per second. The next step in our project is to evaluate our alternative to make sure that our vehicle can take off from the Martian surface and get back to into orbit, so they can rendezvous and head back to Earth. We have to investigate the best way to produce thrust, making sure it's efficient and reliable, because that's what will get our vehicle moving into the harsh condition of Mars. The ion thruster xenon emerged as the front runner in our produced thrust parade study, boasting a remarkable score of 75%, which can be attributed to several key factors, such as redundancy and reliability, as it scored perfect 5 out of 5 in these criteria, show its unique robustness and consistency, as they are crucial for this mission. Additionally, with stability rating of 4 out of 5, the ion thruster proved itself to be steady and reliable, and vital for maintaining precise control and stability in the Martian environment. However, it scored lower in weight and cost, achieving 2 out of 5. It's essential to consider the trade-off. The ion thruster higher weight and cost are offset by its unmatched reliability and performance, which ultimately make it the ideal choice for this vehicle produce thrust needs.
It's Landon, and I'm now going to talk about proposing a suitable concept. So, as outlined in our prior concept of operations, we have interesting features we seek to implement, which make our project quite unique. So we have employment of composite materials, oxygen generation of Martian surface, and high packing density, to name a few, that will make our mission uniquely successful. We have a suitable concept here presented in a graphical form. So there's 2 landers, which will have the SLS 8.4 meter fairing, and during the EDL phase, they have a heat shield and a hypersonic inflatable aerodynamic decelerator, which will serve to bring them very close to the Martian surface, about 1 kilometer. And then once these 2 components are ejected, then there's the lander fairing, which is jettisoned to reveal payload containers, which each have radially mounted parachutes, which allow the payload to land safely on the surface of Mars. And also there's airbags on the bottom to cushion their descent and landing. And each of these will have all the required mission components. So we have the MAV and 1 lander surrounded by these payload containers, and then in the second lander we have the fission power unit and other supporting equipment that is required.
Next, let's have a look at the verification matrix for some of our requirements. Now, these requirements were shown in the SMART requirements slide a little bit earlier. These requirements would have to be verified at each step of the engineering process via different methods. For some of the more complex requirements, such as the landers having to land a maximum distance of each other, this would have to be analyzed and tested via models. Or, for example, the landers having to carry 25 tons inside its inner cavity down to the Martian surface and survive all of the rigors of a Martian launch. These would have to be tested on the vehicle or assembly level, but some of these requirements requirements, such as the ability to keep the internal pressure controlled, only need to be demonstrated. Or, for example, having the launchers have that maximum diameter of 8.4 meters, that can only be inspected. So these requirements, some of them are hard, some of them are easy, but all of them can be solved in their own unique way. Now, as for these risks, there are risks associated with this mission, as there are with any mission. For example, there are some risks that have a very high likelihood of happening. For example, radiation sickness of crew members. In deep space, there is no Martian magnetic field, so the crew members would be exposed to high levels of radiation. This would have to be accounted for via radiation hardening of the outer hull. However, there are also the extremely unlikely but high consequential risks, such as the outer hull being breached or the structural joints of the lander becoming damaged. These are also scenarios we have to take into account, and the landers would have to be specifically engineered to avoid these risks. Here is a risk matrix showing where all these risks are at the point of taking into account their likelihood and their consequences of the risk coming into play. So as you can see, nothing too bad, but definitely something that will have to be engineered in the near future. In conclusion, our mission is to build a dual vehicle Mars lander, two landers between which carry 25 metric tons. So they will be completed by 2040. They'll make travel to and from the Martian surface easy, and they'll be able to transport cargo and samples to and from Martian orbit. With this technology, we will be able to expand the horizons of what is possible with Martian exploration. Thank you.